In this section, we're going to explore how you'll be able to find the best performing materials for a monokok chassis. Similar to how we did this in the previous section, for the space frame chassis, we're going to be using the systematic material selection methodology popularized by Professor Ashby, which allows you to do this more efficiently, helps you inform your decision-making process, and allows you to justify your choices in the competition. This video assumes that you're familiar with the Ashby methodology and the concept of material performance indices. Just in case you're not, please feel free to check out the innovation courses shown on the screen, which are relevant to these concepts, and you can find the links for these down in the description.
Starting with the categorization of the different design requirements within the systematic material selection methodology, we can see that when it comes to the composite panels that comprise the monokok chassis, when considering the frontal impact loading condition, the front and top panels experience the highest stress and they are loaded in bending. So in terms of the function of this component, we can consider the panels to be in a stiffness limited design and for simplification reasons, we can consider them to be panels in bending. In terms of the constraints, we have a couple of material attributes that would help us in narrowing down our pool of materials that we are selecting from. As an example, we're going to narrow down our selection materials to only looking into polymer matrix composites. The rule book of the Formula Student competition provides a minimum for yield strength for the materials that will be used for the monokok. As the minimum, we have 305 megapascal, which is coming from the rule book. In terms of the service temperature range that we expect the material to be able to withstand, we're going to look into materials that are resilient against temperatures of between -20 and 90 degrees. And in terms of objectives, what we are trying to do in this material selection project is to identify materials that have the lowest possible weight as well as the lowest possible cost of material. So the performance indices that are identified on the screen are relevant to these two objectives. And when we are looking into materials with optimum lightweighting potential, the first performance index would be helpful, which is density of the material divided by its flexural modulus to the power of 1/3. And when we are looking into materials that have the highest cost-saving potential, we are going to be looking into the second material performance index, which is essentially the price of the material per kilogram times its density divided by its flexural modulus to the power of 1/3. And we're going to be using these two performance indices to compare these materials in terms of their performance for this application. In this part, we will explore an example workflow of how we can find the best performing materials for a monokok chassis. And to do so, within ANSYS Granta Selector, we can use one of the core functionalities housed in the top toolbar, which is called Chart Select. This is where we are able to create visual charts to compare materials in terms of different attributes or run material selection projects. So let's click on Chart Select, and you can see we are directly within a selection project now. The first thing that we need to identify is what is it that we are trying to select. So here, as you can see, you have access to all the different databases and data tables that are available in the software. For example, if you're working with Material Universe, which we are in this case, you are able to essentially focus on all the materials that are available in this database or a specific category of materials like ceramics or polymers or metals, or we have the option to create our own subset of materials. And this is what we are going to be using for this case study. So let's click on that. So the first thing that we can identify here is that we want to be looking into only bulk materials. So we can choose this option. And then for this case study, as previously mentioned, we are focusing on specifically polymer matrix composites, which can be found under two categories mentioned here. One of them is within the hybrid materials in composites folder. You can find the polymer matrix subfolder. So let's choose this one. And you can also find polymer matrix composites in the polymers category. So I'm going to choose this category as well. And we can click on OK. And as you can see, by doing so, there are 845 materials that essentially we are choosing from. So as a first step, we can create a visual chart to compare these materials in terms of the material performance indices that we had identified previously in the slide. So in order to create a chart, we can click on Chart Index, and the software asks us to fill in what we are trying to show on the Y and the X axis. So for the Y axis, I'm going to consider the material performance index that is relevant to minimizing weight, which is, as explained before, density divided by flexural modulus to the power of 1/3. We have two options to essentially implement this material attribute combination on the Y-axis. One is using the advanced option and the other one using the performance index finder. So for the Y-axis, I'm going to showcase how we can do that through the advanced option. Let's click on advanced. Here we can essentially construct any combination of material attributes that is relevant to our selection projects. So in my case, I would like to look into, as mentioned, density divided by flexural modulus to the power of 1/3. So density can be found under physical attributes. There you go. So if I double click on the label, density would pop up in the screen, and that would be density divided by flexural modulus, which is a mechanical property. And there it is. And this needs to be to the power of 1/3. There you go. All right, so if we click on OK, now we have this attribute on our Y-axis, and for the X-axis, of course, we can do the same thing and use the advanced option here, or we can use a bit more straightforward option that we have in selector, which is performance index finder. This helps you identify what is the relevant performance index for a specific objective and function for the application that we have in mind. So if I click on performance index finder, we need to identify the function of our application, and as previously mentioned, in this case we are dealing with panel bending, but as you can see, there are many different other functions that are available in the software on the mechanical side for abrasion resistance applications, thermal, electrical, and barrier applications. So let's stick to panel bending. We need to identify what is the limiting constraint. As mentioned before, we are dealing with a stiffness limited design. So let's stick to stiffness, and we are trying to optimize cost. So if I click on cost, you can see the software automatically identifies what is the right performance index the right performance index for this objective. So if I click on OK, you can see that we have these two performance indices on the Y and the X axis, and we can easily compare these materials in terms of these two combination of attributes. Now, of course, we are now dealing with more than 800 materials. We need to narrow down our selection, and to do so, we can start implementing and applying our constraints. In order to do so, we can use the limit stage. So if I click on limit, you can see that we are presented by all the different categories of material properties. And if we have a minimum or a maximum for each of these, we are able to apply them here. And by doing so, we can narrow down our pool of materials that we are selecting from. So one of the constraints that we had was a minimum value for our yield strength, which was 305. And another constraint that we are dealing with here is a thermal property constraint in regards to a range of service temperature that we want our material to be able to withstand. So we wanted to this range to be between -20 and 90 degrees. And so we can put in these relevant values. There you go. And by clicking on apply, you can see that we drop down from 845 materials down to 34 materials. So if I go back to my chart, you can see that most of our choices have now gone gray. They are not colorful anymore. This is because they have failed our selection stage. They didn't meet the standards of our constraints. So we can remove them from our chart by clicking on Hide Failed Records, and we can focus on the materials that have passed our selection stages by auto-scaling. So here we can see that we are in a multi-objective optimization scenario in which we are trying to find materials that simultaneously have optimal lightweighting and cost-saving potential. And as always, in these types of scenarios, using a Pareto front could be helpful. And so we can create a Pareto front by using the curve option on the top toolbar, and we can manually draw a Pareto front on our chart. We can move this curve towards our materials. As the theory goes, the choices that are closer to a Pareto front in a multi-objective optimization scenario are what we call non-dominated solutions, and these are equally suitable in terms of being optimal for a specific application, like in this case. So we can start labeling the materials that are closer to our Pareto front. So we can see that we have a polyester matrix composite, which has glass fiber as its second phase. That's one of our optimal materials. We also have a epoxy with a high strength carbon fiber as its second phase. And finally, we have a cyanide ester, which is filled with, again, carbon fiber. So these are the three optimal materials that we have on our chart. We can go another step further and try to distinguish between the composites that we have available on this chart, which have a carbon fiber or fabric as their second phase, as opposed to aramide polymers or glass fibers as their second phase. So how do we do that? Well, we can use a trick in which we can create another limit stage. And in this limit stage, we can go into composition overview. Here we have the option to essentially narrow down the materials that we have on our chart onto a specific set of materials that have, for example, a specific type of filler or reinforcement. So I can choose here to only look at materials that have carbon as their reinforcement or filler. I can click on apply. And by doing so, we can see that there are only 19 materials left on our charts. So if I go back, we can see that these are the ones that have either carbon fiber or fabric or prepeg as a part of the essentially as their second phase within the composites. So what am I going to do here is that I'm going to change the color of these materials. So I'm going to select all of them on our results table. There you go. I'm going to exclude the two thermoplastics that we have on the chart and focus on the composite materials, the ones that are categorized as composites in Selector. So I right click on these. And here you can see that we can change the record color to lime in this case. So we can easily distinguish the materials that have carbon as their second phase, and then I can just untick this third stage, bring back the materials that we had before. And so by using this trick, we can easily distinguish between the composites that have carbon as its second phase with the ones that have aramid polymer or glass fiber as their second phase. So that's essentially the first stage of our material selection, in which we have compared these materials in terms of their lightweighting and cost-saving potential. But of course, when you're in a real-world material selection projects, there are other attributes of materials that have real-world impact. For example, when it comes to sustainability of materials or their environmental impact, there are specific material attributes that can be taken into account when you're trying to select materials for a specific application. In this case, for example, I'm going to create another chart, and this is going to be a bar chart. So on the y-axis, I'm going to populate it with the carbon footprint of these composites, which can be found under the category of primary production energy and CO2 footprint, as well as water consumption. So as the attribute, I'm going to look into the CO2 footprint of the primary production for the typical grades of these composites. So when I click on OK, a bar chart pops up, which includes all of the 845 materials on the chart. I can again remove the unsuitable materials, the failed materials from the chart, and focus on the ones that essentially have passed our selection stages. So obviously, looking at this chart, we can easily see that the carbon fiber composites are compared to the fiberglass as well as aramid polymer composites. They have far more carbon footprint. The carbon footprint is far higher, and so if environmental impact of these materials is important to us, this is a good indication of whether we can essentially choose a carbon fiber as opposed to a glass fiber composite. Now, in order to do a final assessment, obviously we can take all of these different aspects into account: the technical side, the economic side, as well as the environmental aspect of choosing these materials. And we can see that when focusing on the lightweighting and cost performance of the screened composites, the best performing materials, as you can see on the screens, are as follows. So we have the polyester e-glass fiber. We have the epoxy high strength carbon fiber, which is unidirectionally pre-pegged with unidirectional layup. And we have the cyanate ester with carbon fiber, which is unidirectionally pre-pegged and unidirectionally with unidirectional layup. The first option, however, is unsuitable for this application because it pertains to the composite in the shape of, as you can see, a pultruded rod and not a panel, which is what we have assumed this monocoque to be. However, there is another glass fiber reinforced polymer on the chart which has roughly the same performance, and this is the polyester polyester matrix composite, which has e-glass fiber as its second phase. It is in the form of a woven fabric with 65% weight percentage of glass, and it has biaxial layup. So this has roughly the same, at least in terms of its cost-saving performance, as well as the light-weighting potential. It is roughly similar to the other glass fiber composites that we have on the chart. And so for this application, if we would like to use a glass fiber composite, this option, the polyester e-glass fiber, is probably our best choice. But to make a final decision, we need to consider our prioritization of lightweighting versus cost performance. So if we are able to justify the high cost of carbon fiber reinforced polymers on the chart, the ones that are shown in green at the moment, because of their lightweighting performance, of course, they seem to be preferable, then the epoxy with high strength carbon fiber, as well as the cyanide ester, seem to be our final choices. If not, and we are mostly, conscious of the cost of our components, then the polyester with e-glass fiber would be our final choice, right? However, as mentioned before, the environmental impact of these materials is, of course, important as well. And so when we bring that aspect into consideration, if that is something that is important to us, then obviously glass fiber composites are much more preferable to the carbon fiber composites. And so on the whole, it might make sense to actually have the polyester e-glass fiber to have as our final choice. Again, if the environmental impact is important to us and if the cost-saving performance of these materials are more important to us than their lightweighting potential, right? Now, we can also go into the datasheet of this polyester matrix composite and see if we have, roughly similar applications that this material is being used for at the moment. And we can check that within the typical uses of this material, we have automotive applications, car bumpers, body panels, and truck cabs. So very similar applications that we want to use this material for when we are looking into the materials that would be suitable for a monokok chassis. These material is already being used for similar applications. So it is not a far off choice that we have come up with, but again, the discussion that can be taking place after going through this systematic material selection methodology depends on the prioritization of whether lightweighting is more important to us, or cost performance, or the environmental impact of these materials, or a combination of these. Okay, so that's the material selection step of this course for the monokok chassis. Let's move on to the next stage.